guys, welcome back to Wong Chemistry channel. For this video, we are still talking about 4.3 orbital overlap and hybridization. For the third part of this topic, we are going to talk about only one thing, hybridization process. So we are going to move on from the type of hybridization to the hybridization process. Okay, so let's check it out. Let's recall on the step to determine the hybridization in your video in part 2. So in the part 2 video, we have discussed on how to determine the hybridization. As always, we start with the correct Lewis structure, determine the electron domain. Alright, I have give you many examples on how to determine the electron domain. And then from the electron domain, you can determine the type of hybridization for your central atom. And in this video, we are going to continue from here. From the type of hybridization that you have determined, that you already know, we can work out the hybridization process. In the other words, we can show how the hybridization process is obtained. Make sure you have your pen, papers ready with you and do it together with me. Then it will be much easier to understand. Alright? Alright, kind reminder over here, this is the electron domain and its hybridization with the correct geometry. We have talked about this in your previous video. This is just to recap your memory, just to make sure you know all this. Okay? We have talked about how do we get the electron domain and how do we determine the hybridized orbital and the geometry in the previous video. Okay? So next, what is actually hybridization process? Hybridization process is a process that you show how the hybridization is happening by using orbital diagram. So we are going to draw a lot of orbital diagram, okay? And bear that in mind, the hybridization that we show is only for central atom as always. So for the central atom, there are a few steps. You must start off always with the orbital diagram for the valence electron of the central atom only. And that we call it as ground state. Okay? So you draw the orbital diagram of the valence electron for the central atom. And then you are going to excite the electron to a higher energy orbital if it's needed. I will show you when it's needed. Okay? And that is what we call excited state. So you have your ground state moving to your excited state right now. Last but not least, you are going to draw the new hybridized orbital form, which is your hybrid state. So for the central atom, we have 3 stages. 1, ground state, excited state, moving all the way down to your hybrid state. So that is what we are going to do for the central atom. How about terminal atoms? So for the terminal atoms, we are not showing the hybridization process, but it's very important for you to draw the orbital diagram for the valence electron only. In the other words, for the terminal atom, all you need is the ground state of the orbital diagram for your valence electron only. Okay? For the central atom, is the only one that we show hybridization process. Okay? By the way, make sure you remember what is orbital diagram. How to draw orbital diagram. Orbital diagram is this, if you remember. Alright, this is what we call orbital diagram. You have your 2s and then you might have your 2p, all this. That is what we call your orbital diagram. If you are having a 3D orbital, so your 3D orbital should look something like this. Okay, 5 boxes, 5 different arrangement of the d orbital. So this is what we are going to do a lot in this hybridization process. Okay, so let's move straight into the first example that we have is beryllium fluoride, BeF2. So bear that in mind, before you can go for your hybridization process, you must actually draw the correct Lewis structure, determine the electron domain, identify the type of hybridization and the geometry, then only we can move into your hybridization process. So let's start with the Lewis structure very quickly. As we all agree, by this stage at this video, you should be very good in drawing your Lewis structure and determine the hybridization of your central atom. So in this case, I'll just draw it very quickly just to recall your memory. From the correct Lewis structure that you have drawn, we can then move to electron domain. From the electron domain that you have identified, which is 2, from the electron domain, we can then move on to the type of hybridization for your central atom. So, from the type of hybridization, straight away, you know that the geometry is linear. Okay? So, we are now having the things that we want. We know the type of hybridization is what already, which is your SP. So, from this type of hybridization, we can then move on to the most important thing for this video, hybridization process. So, I'm going to show you how to start with the hybridization process and how do we proceed in the hybridization process. So, the hybridization process, the first thing that you need is actually the valence electron of the central atom in orbital diagram. So, starting the first stage, which is your beryllium. Your beryllium right now is in ground state. So, the ground state means just the valence electron of beryllium in the orbital diagram. So, the orbital diagram for the valence electron of beryllium is this, with 2 electrons in 2s. But because the type of hybridization that we have determined a moment ago, we know that your beryllium is a sp, where you need one orbital from the s and another orbital from the p. Therefore, in this beryllium ground state, you still need to draw the 2p orbital, even though we don't have any electron in that, because we need to use it for this hybridization process. Next, moving to the beryllium, next stage is your excited state. So, what is actually excited state and how do we do the excited state? Simple. We have already identified the type of hybridization of beryllium in beryllium fluoride, which is your sp. And we know that, guys, sp means we are going to take one from the s and one from the p. But guys, look at the p. The p orbital right now is empty, but I need the p orbital to have electron because of your sp hybridized orbital over here. So, what do we do to make sure the p orbital in the beryllium having electron? That's why you have your excited state. We are going to excite one of the electron in 2s into the higher energy orbital 2p. Okay? That's why you have what we call over here excited state. So, in the excited state of beryllium, what will happen in your 2s is the 2s will only left with one single electron, and in the 2p orbital, one of the electron will be already moving up to your 2p orbital. Alright, it's being excited to the 2p. Alright? And then you can see over there, your sp orbital can be produced when we have your beryllium hybrid state. So your beryllium hybrid state over here should look something like this, where you are taking one from the s orbital and another one from the p orbital. Just like this. And right now, it's no longer 2s and 2p because we already hybrid them. We already mix them together. Therefore, the name of this orbital should be sp. See that? Okay, as simple as that. And then, the number of boxes or the number of orbitals shall remain the same from the beginning till the end. So for those empty orbital or the orbital that is not involved in the hybridization process, make sure you label them. This guy will be the empty 2p orbital. Okay? And all this, all the way here, is the hybridization process of the beryllium central atom, moving from the ground state to the excited state to the hybrid state. So the ground state is just the valence electron in orbital diagram. The excited state, we are going to move the electron from a lower energy orbital to a higher energy orbital. Last but not least, in the hybrid state, we are going to mix them together to form a new set of hybrid orbital. Okay? And we are not done yet because that is only for your central atom. Right now, we need to draw for your terminal atom, which is fluorine. But for the fluorine, you only need to draw for the ground state. In the other words, you only need to draw the valence electron of fluorine in orbital diagram, which is something like this. You should know by now the valence electron of fluorine is located in 2s2 and also 2p5. So your 2p5 according to Hans rule singly first, and then pair up according to Pauli exclusion principle. So that is how your orbital diagram of the valence electron for fluorine at ground state, which is 2s2, 2p5. Okay? So hybridization process is this entire process. Alright, this whole thing is what we call hybridization process. Moving from the central atom ground state to the central atom excited state to the central atom hybrid state and then to the terminal atom ground state. Okay? But bear that in mind. Your hybridization process must come after the correct Lewis structure, followed by the correct electron domain. After you know the hybridization of the central atom and the molecular geometry, then only you can move to your hybridization process. Can you see the flow? Okay, so it's not something that you can get straight away. No, you need to draw from the Lewis structure, find the electron domain, identify the hybridization, then only you can do the hybridization process. Simple. Okay, it's basically the things that we've been repeating. Okay, next example, we have boron chloride. Okay, so as always, we start off with the Lewis structure. So for the Lewis structure, total valence electron. After the Lewis structure, then we move on to your electron domain. From the electron domain that you have just calculated and determined, from the Lewis structure, from the correct Lewis structure, then you move on to the hybridization. The hybridization obviously is your sp2. Why is that sp2? Because the electron domain is 3. And the geometry for your sp2 obviously trigonal planar. Okay, so we are done with the first step of Lewis structure, and then we move to the electron domain second step, and then we identify the type of hybridization third step. So right now, we can move on to your hybridization process. So like the example just now, your hybridization process over here required orbital, diagram, and valence electron. Okay, so for the central atom boron, the ground state started off with the valence electron of boron that located in 2s2, 2p1. So you have your 2s2 valence electron of boron, and also you have 2p1, which means you will have 1 electron in the p orbital. That is the valence electron of the boron in the ground state. Next, moving to the boron, but we are moving to the excited state. So moving to your excited state, you already need to pay close attention to your hybridization. Your hybridization that you determine from the electron domain is sp2. sp2 means 1 from the s, 2 from the p. Therefore, we are taking 1 from the s and we are taking 2 from the p. But you realize this thing right now is empty. So what do we do in the excited state? As before, we are going to excite one of the electron into the higher energy orbital, 2p. Okay, so for the excited state of boron, it will look something like this. Your 2s will only left with 1 electron, and then your 2p will have an extra electron placed into your 2p orbital. The original 1 electron and then the extra 1 electron. Okay? And why do we need 3 single electron? Look at your boron central atom. Your boron central atom having 3 sigma bond. Guys, do you remember sigma and covalent bond? Which means one of the electron in this bond is actually coming from boron. So boron need 3 single electron to pair up with 3 chlorine. That's why you need to excite this electron in the 2s into the 2p. And having 3 single electron over here, guys, is where your boron can have the 3 sigma bond. Now you can see better? Alright? That is the reason why you excite your electron from the 2s to 2p. Because the boron needs 3 single electron for the 3 sigma bond. Makes sense? So, moving to your boron hybrid state. So, in this hybrid state, it's simple as mixing out what you need to mix. So, we are going to take 1 box from the S and 2 boxes from the P. Because from the electron domain, we have identified the type of hybridization is sp2. So, taking 1 from the S, taking 2 from the P. Makes sense? And then we have 1 more box over here which is empty and not involved in the hybridization process that you will label as your empty 2p orbital. Okay, it's not involved in the hybridization process. And this is the hybridization process for your central atom. How about terminal atom? So for the terminal atom chlorine, you only need the ground state. And the ground state valence electron for your chlorine is 3s2. And then 3p5. Put down 5 electron in your 3p. And this right now is the complete hybridization process of your boron chloride. Okay, your BCl3 having boron all the way from ground state, moving to the excited state. And I hope you understand why we need to excite the electron right now. And then moving to the hybrid state where you mix up the orbital to form this new set of orbital that you have determined, that you have proven that you want from the Lewis structure. And then the ground state for your terminal atom as always. Alright? Easy. Going to the second example, you should be able to see very, very clearly right now. Okay? Next example is quite simple. Your example 3, methane, CH4. Very simple structure. Okay? So, let's start off with the total valence electron and your Lewis structure. Lewis structure done, moving to your electron domain. From the electron domain that you have determined, then we can go for the hybridization. So the hybridization that you determine is sp3 over here, and the geometry is tetrahedral. Okay? Just before we move on to the hybridization process, looking at your sp3, you know that you're taking 1 from the S and then you're taking 3 from the p orbital. Okay? So you should have something like this as your sp3. Okay? Agree? So same, before we proceed to the hybridization process, let's take a quick look at your central atom. So, central atom in the Lewis structure having 4 sigma bond. And we know that in the 4 sigma bond, in every sigma bond, 1 of the electron is contributed by the carbon. Agree? Therefore, how many unpaired electron or how many single electron does the carbon need? Carbon right now needs 4 unpaired electron in the excited state. Agree? Carbon needs 4 unpaired electron in the excited state so that the carbon can form 4 sigma bond with 4 hydrogen atom. So you can basically guess how should your hybridization process look like from the Lewis structure and also from the type of hybridization. See that? Alright. Let's move on to the hybridization process by using again all the orbital diagram. So let's start with that. So carbon, ground state, as always, as you all know, we always start with the ground state, and the ground state over here means the valence electron of carbon in their respective orbital, which is 2s2 and then 2p2. And looking at the ground state right now and also your type of hybridization sp3, we need 1 from the S and all 3 from the P. And we know that we need to excite 1 of the electron to 2p. And guys, why do we need to excite? Remember this? Remember the 4 sigma bond that I said just now? Where the carbon needs 4 unpaired electron. Alright? So we are going to excite the 2s electron into 2p orbital. So the excited state of the carbon in this molecule shall look something like this. The 2s will have 1 electron left, and then the 2p will have a new friend. Okay, so your 2p will have 1, 2, the original 2, and then 1 of the electron that excite from the 2s. Can you see right now? Okay, so obviously for the carbon hybrid state, when we are going to hybrid it, we already know the hybridization that we want is sp3. We know that sp3 means taking 1 from the s and 3 from the p. So the hybrid state of carbon shall look something like this, which is your sp3 over here, having single electron, single electron, single electron, and single electron. And why all the single electron? All the sigma bond that you have in the Lewis structure. See that? Simple. Very simple. Alright? Just one thing, guys. Make sure your total valence electron is correct. Make sure your Lewis structure is correct. If your Lewis structure is wrong from the beginning, all this is gone. Okay? And as always, your hybridization process will move all the way until your terminal atom, ground state. So the ground state of your hydrogen right now is very simple, which is 1s1. Okay? And you are done for the CH4 hybridization process. Simple. Alright? Next, we have PCl5. Just let me quickly show you from the Lewis structure until the molecular geometry. So we are done with the first step of Lewis structure. The second step of electron domain. From the electron domain, you can figure out the type of hybridization. And the type of hybridization for your central atom phosphorus in this question is your sp3d. So we know that sp3d over here means 1 from the s, 3 from the p, and then 1 from the d. Okay? And then looking at the central atom in your Lewis structure, phosphorus having 5 sigma bond, guys. Phosphorus having 5 sigma bond. And most important thing, it means every bond having 1 single electron from the phosphorus. Therefore, phosphorus need how many single electron? Phosphorus will then need 5 single electron to ensure that it can form 5 sigma bond in this compound. Let's move to the hybridization process. And the hybridization process, as always, will start with what? We will then start with the phosphorus ground state. And the phosphorus ground state over here, having 5 valence electron, where 3s2 holding 2, and then 3p3 holding 3. So this is the 5 valence electron phosphorus having. But I hope you remember, the type of hybridization right now is sp3d. In the other words, we are using 1 from the s, 3 from the p, and 1 from the d. Therefore, you need to show the d orbital of your phosphorus as well, even though it's empty right now. It's only empty at this moment. And after so many examples, you should roughly know your excited state is why and how. So, your excited state right now, obviously, you're going to move 1 of the electron in the 3s all the way to your 3d. Why all the way to your 3d? Because your 3p is already having all single unpaired electron. And we need 5 single unpaired electron. So you need to excite 1 of the electron from the 3s to the 3d. It's just the same thing, guys. So you have your 3s over here, 1 single electron. And then you have another 3p that is pretty much unchanged, having 3 single electron. And for your 3d, that was empty just now. Right now, your 3d will have a new friend, which is the electron that excited from the 3s. Can you see that? And for the hybrid, we need to take 1 from the 3s, 3 from the 3p, and 1 from the 3d. So for the phosphorus hybrid state, for this hybrid state, what are you going to do? Is you are going to hybrid the orbital that you need to hybrid. Okay? Which is your sp3d. And your sp3d should look something like this. Simple. Easy. And we are not done yet because we have empty orbital over here. So make sure you draw the empty orbital clearly and label as empty 3D orbital. And you are done for the central atom. While for the terminal atom, as we all agree just now, we only show the ground state. So the ground state for the chlorine is your 3s2, having 2 electrons in the 3s, and then having 3p5. And this is the complete hybridization process of your PCl5. Simple, easy. And guys, last but not least, a quick one on SF6. Alright, a quick one on your SF6. So we are done with your Lewis structure. We can identify the electron domain, and the electron domain is 6. And from that, we can identify the type of hybridization and the hybridization that we have right now, sp3d2. Okay, so your sp3d2, obviously 1 from the S, 3 from the P, and 2 from the D. Okay, so we are going to have something like this. 1 from the S, 3 from the P, and 2 from the D. Agree? And then looking at the Lewis structure centratum, guys, sulfur right now, 6 sigma bond. So everybody knows in 1 sigma bond is 1 electron contributed by the sulfur. In the other words, sulfur need to have how many single unpaired electron? Think about that. Let's jump into your hybridization process. And from that, you need to know already how many single electron that sulfur should have. Let's start with the sulfur ground state. Knowing that sulfur having 6 valence electron located in your 3s2 and also located in your 3p4. Okay? And we know that in the hybridization, we know that we are going to use D. Therefore, you need to draw the 3D that is currently at this moment empty. So you have your 3D over here, which is empty at this moment at ground state. So your sulfur moving to the excited state. Look at your ground state, guys. Look at your ground state. How many electrons that need to be excited? At this moment, we need to excite 1 from the 3p, moving up to 3d, and we need to excite another 1 from the 3s to another 3d, so that you can have 6 single unpaired electron for the sulfur. See that? So your excited state shall look something like this. 3s will only have 1 electron left. 3p over here will have 3 single electron. While in your 3D that were empty a moment ago, right now is no longer empty. Your 3D will have 2 single electron, 1 from the 3p, another 1 from the 3s. See that? Next, your sulfur hybrid state. Okay, from your sulfur hybrid state, obviously, we are going to mix up 1 from the S, 3 from the P, and 2 from the D orbital. And that is my sp3d2. They are no longer 3s, 3p, or 3d. When they start to mix up together, they will be named as sp3d2, that having single electron in each and every one. So you have 6 single electron for the 6 sigma bond. And therefore, make sure you don't left out the empty 3D orbital that are not using in this hybridization process. And last but not least, your fluorine ground state as the terminal atom. So the ground state of fluorine, as you all know, is located in the 2s2 and 2p5. So let's draw quickly on the orbital diagram of the fluorine ground state 2s2, 2p5. And this is the complete hybridization process for your example SF6. Moving all the way from your Lewis structure to the electron domain to the type of hybridization, and then starting from your hybridization process of the ground state, just the valence electron in the sulfur. Moving to the excited state where the electron will be excited into the higher energy orbital. In the hybrid state, you are mixing up the orbital that you need. So you mix up the 1 from the S, 3 from the P, and 2 from the D to produce a new set of orbital sp3d2. And last but not least, your fluorine ground state as the terminal atom. Okay? And that's it for hybridization process. Simple. There will be more example in other videos talking about the central atom that having lone pair or the central atom that having double bond. So make sure you check out the other video and try to do the others example. Okay? If you still have any question on the hybridization process, drop it in the comment below and I'll get back to you as soon as I can. Make sure you like the video, share it to your friend and subscribe to my channel. Thank you for watching and I'll see you again in the next video.